Good afternoon, everyone, and welcome to today's Museum of Science live program, Virtual Planetarium Exploring Space. Today, we'll be talking to a couple of our astronomy educators about the night sky. My name is Mike, and I'll be your moderator during today's session, which means that I'll be fielding all of your questions and predictions that you might ask our educator. To ask a question or share something, just press the Q&A button at the bottom of your screen and include your name and age if you'd like a shout out if we end up using your question on air. If you'd like to see captions, you can click on the closed captions button at the bottom of your screen and select show subtitles. And if you're joining us on Facebook, we're so pleased that you're tuning in today, but please know that we cannot see your questions or observations on that platform. So at this point, I'll invite our educator to turn on their cameras, introduce themselves, and then we will get started.
Hi, everybody. My name is Katie. My pronouns are she and her, and I will be your guide today as we explore space, but all I will be doing is the talking.
Hey, everybody. My name is Talia. I also use she, her pronouns, and I will be doing a little bit of flying through space for us today.
Awesome. Sounds good. So Talia is going to be using a program called Worldwide Telescope, and so she can bring us into space. Awesome. So right now we're getting a view of our solar system, from above or below, just from the outside, looking at the various objects in the solar system. And just to kind of get us started, maybe do a little warm up, go ahead and type into the Q&A different objects that you would find in a solar system. So think about what you would see, looking up in certain parts of the sky at night or during the day.
We're starting to see some answers from our audience. Lots of stars, some planets, sun or our sun or other suns out there, asteroids, comets, the asteroid belt, black holes. That's an interesting answer. Awesome.
Awesome.
Yeah, lots of good things.
Yeah, those are great answers. So in solar systems, in our solar system in particular, we've got planets and moons and asteroids. I know some of you mentioned those, comets. The sun is also part of our solar system, but other stars and things like black holes, I know that was mentioned as well, those are not part of our solar system. Our solar system consists of the sun right at the center. Then we have 8 planets. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you can actually see their orbit lines here. That blue orbit line that's second to last is the orbit of Neptune. This also includes the orbit of Pluto. So for anybody feeling nostalgic about Pluto and, maybe a little bummed that it's not a planet anymore, you can see its orbit line out there. So those are kind of the main objects in our solar system. And then, of course, we have the asteroid belt in between Mars and Jupiter. And then there's some more objects even kind of out floating where we are from our perspective in our solar system. Those objects called Kuiper belt objects. It's kind of like the asteroid belt. So I just wanted to give a little bit of an overview of our solar system because today we're going to be talking a lot about the sun and the sun's effects on the Earth, for example, and other parts of the solar system. So as I mentioned, the sun is in the center there, and all of the planets, all those circles that you're viewing are the orbits of the planets going around the sun. And the reason that they're orbiting around the sun is because of gravity. So the sun, in comparison to the planets in our solar system, is extremely massive, way more massive than any of the planets. And so it has a very strong gravitational force, and it's able to hold on to a lot of objects like planets and moons and asteroids and all those other things that we were talking about, just because of how massive it is and how strong its gravity is. Now, I have another question for you that you can type into the Q&A, type in your answer. What do you think the difference is between a star and a planet or a moon or another object that you'd find in the solar system? And I did mention some, some differences, right? Like size and gravity and things like that. But what actually makes a star a star? And if you don't know the answer, by the way, just feel free to type in, I don't know, or I'm unsure, or type in a question mark, because that is totally okay, right? If we knew everything, we probably wouldn't have science at all. So just feel free to type in what you're thinking into the Q&A.
We've got a few answers already, Katie. We
Great.
have some answers that stars are made of gas, but planets are mainly made of rock. That stars will burn out someday. Stars give off heat and energy. Planets are solid. Someone's even identifying the states of matter that are in stars, gas and plasma. And also that planets are smaller and they don't make their own light.
That is awesome. Those are all really great observations. To anyone talking about plasma or really, really hot gas, that is part of it. So it doesn't actually have to do completely with what a star is actually made of, because a star is basically very, very hot energized gas. But we also have gas planets, right? So it's not necessarily because they're made of gas, but it's more that stars make their own light. They have their own energy source that then heats up all of that gas and energizes that gas and causes it to actually be plasma. Planets don't have this internal, well, sometimes they have an internal energy source, but it's not the same as a star. They're not actually making enough energy to emit light. They're just reflecting light from the star that they orbit, or in this case, the sun. So if we want to talk about this internal mechanism and how a star is making its own light and heat, we have to talk about a process called nuclear fusion. And to talk about that, we have to talk about what stars are actually made of. And so some folks had mentioned gas or plasma, but the actual elements that a star is made of is mostly hydrogen and helium, which are the two lightest elements on the periodic table. And the process of nuclear fusion is basically taking these very light elements like hydrogen, putting them under immense pressure and temperature to the point where they start to just collide. And sometimes they squish together, they smash together, is more like it, and they make helium and release energy at the same time. And that energy is the light and heat that comes from stars. So I'm going to pause there before we keep going and just see if we have any questions so far.
We have a few good ones. Jacob, age 5, asks, why do stars sometimes explode?
Ooh, that's a really good question. So that is kind of where I'm headed. And stars do eventually run out of fuel. That nuclear fusion process can start to slow down as a star ages and starts to run out of these lighter elements. And eventually, once it runs out of fuel completely, it will die. And it can either, depending on the size of a star, it can either just kind of expand and shed its outer layers of gas, or if it's a really, really massive star, it can explode in a supernova. So in order for a star to go supernova, it's got to be running out of fuel, and it's got to be really massive, way more massive than our sun. Our sun is a pretty average star. You would need a star that's at least 8 times as massive as the sun in order to go supernova.
And you were mentioning some of the planets in our solar system, Katie.
Mm-hmm.
Rusty asks, why is Pluto no longer considered a planet?
Yeah, another great question. So Pluto was considered a planet from its discovery back in 1930 to 2006, when astronomers decided that it no longer fit the definition of a planet. And so nothing actually happened to Pluto. Like, it didn't explode or run away to a nicer solar system or anything like that. Pluto is the same as it's always been. It's just what we call it is different. So back in 1930, the only object beyond Neptune in our solar system, remember, just in our solar system, our little neighborhood here, was Pluto. That was the only object astronomers knew about. And it stayed that way for a while until like the late 1990s and 2000s, when they actually started to discover that Pluto is not alone out there. Pluto has a whole bunch of neighbors that are just like Pluto. So Pluto's a very tiny world, very small, icy. If you were to kind of plop it onto a map of the United States, its diameter would only take up about half of the United States. So it's very, very tiny. And so it doesn't really fit in with a lot of the outer planets, right? Jupiter, Saturn, Uranus, Neptune, they're all very massive gas giants. And Pluto's just a tiny little snowball. But all of the neighbors around Pluto, all these other objects, are also very small and icy. And it turns out that there are thousands of these confirmed objects, and there are presumed to be hundreds of thousands of these objects. And Pluto's orbit is kind of wonky, and it's orbiting with all these other objects out here. So it's basically just part of a new classification of objects called the Kuiper Belt, which is similar to the asteroid belt, just farther out. It's out past Neptune. And this isn't the first time this has happened. A long time ago, back in the early 1800s, we had 16 planets in our solar system because astronomers were finding planets in between Mars and Jupiter. But then over time, they started finding thousands of these objects. And so it turns out what they were discovering was just the asteroid belt. And so instead of calling some of these objects planets, they started calling them asteroids and made this new category of objects. So it's just because Pluto's out there, very small, icy, orbiting with a bunch of other objects, that it's a lot more similar to than it is to the planets. Sorry, I know that was a really long answer. All right, well, if there are any other questions at this time, we can keep talking about the sun. So we'll get right back up close. Now, we were talking about how stars have an energy source and what they use for fuel. It's basically converting hydrogen into helium and releasing energy. That's the process of nuclear fusion. And if you're wondering, well, how do we know that this is happening? How do we know what stars are actually made of? All of this kind of stuff. That's a great question. And it all has to do with observing the light from stars, which we can do with telescopes. So I'm actually going to switch over to some visuals that I have. And I'm going to show you, let's see, we're going to look at the electromagnetic spectrum. All right, so hopefully everybody can see this diagram that I have up. So the electromagnetic spectrum is light, pretty much. Now, our eyes can only perceive a very small part of the entire electromagnetic spectrum. And you can see that in the rainbow, the colors of the rainbow. That's the part of the whole spectrum that we can pick up with our eyes. But as you'll see, there are actually many other wavelengths of light that we can't see with our eyes. And those would be anything to the left or to the right of the visible part of the spectrum. If we get anything longer than a red wavelength, so infrared light, microwaves, radio waves, we can't detect those with our eyes, nor can we detect ultraviolet light, X-rays, nor gamma rays. And so we use special instruments on telescopes in order to pick up these other wavelengths of light, because stars don't just emit in the visible spectrum, they emit across the entire spectrum. And when we look at the light across the entire spectrum, there's a lot that we can tell about a star. We can tell what it's made of, and knowing what it's made of can tell us how far along it is in its life. So like our sun, for example, is, I mentioned it's an average star. It's also about halfway through its life. So it's 4.5 billion years old or so, and it has another 4.5 billion years to go. So it's kind of right in the middle of its lifespan. And some of the telescopes that we use to observe the sun and to take the spectra of the sun are, well, one of them is the Solar Dynamics Observatory. So I'm going to show you a video of our sun from the Solar Dynamics Observatory. So this particular spacecraft is in orbit around the Earth, and it observes the sun in other types of light that we cannot see. And actually, I'm going to show you one other video first. So this one, you can actually see each little slice there is its own wavelength of light. So this just has a whole bunch of them there. And you can see that in certain wavelengths, you can see different features. Like in some, you can see the magnetic field, and others, you can see a lot of the sun's atmosphere. Some of them you can see sunspots in. So each type of light gives you clues about a star. All right, so we'll go back to the Solar Dynamics Observatory. So this is a NASA spacecraft. It's in orbit around the Earth, which I think I already said. But this particular video is viewing the sun in ultraviolet light. Now, if you were to look at the sun in visible light with, first of all, you should never actually look at the sun with your eyes. You need protective equipment, so like a very special filter that's specifically made for observing the sun, or like a welding filter, something like that. It has to be fully approved to view the sun because you can really damage your eyes. So if you were to look at the sun with all of these special filters just with your eyes, then you wouldn't see anything that looks like this. You wouldn't really see the magnetic field of the sun, those little loops that are popping out. You would pretty much just see a orange sphere, and occasionally you might be able to see some dark spots on its surface. But in this view, we can see loops, and we can actually see plasma traveling along the magnetic field lines of the sun. Because the sun is made of plasma, it has a very complex magnetic field. And these loops pop out of the surface all the time, and they get all tangled up. And sometimes they send huge swaths of charged particles and radiation out into space when the loops snap. And we can actually observe some of these, what they're called solar flares. We can observe the effects of a solar flare here on Earth. And so the next thing I want to show you is how we can observe these effects. So you get all of this material coming from the sun, lots of charged particles and radiation hurtling through space, and then it hits the Earth's magnetic field. And the Earth's magnetic field protects us from a lot of that radiation. But a lot of these charged particles travel down the field lines to the poles of the Earth and enter the atmosphere. And when they enter the atmosphere, they bounce around with different particles like nitrogen molecules and oxygen molecules, and they cause them to release energy in the form of light. And so that's how we see the aurora borealis if you're in the north, or the aurora australis in the south. And so we can observe these solar flares by looking in ultraviolet light. And there's some other filters of light, or wavelengths of light, I should say, that can observe other solar events as well. All right, so are there any other questions so far? I have a couple of other things that I want to show you today, but I'll pause for questions first.
We have lots of questions. Many people were asking about the life cycle of stars and how long they last. So I answered that in the chat already. But we've got some interesting questions about other planets. Jacob, age 5, asks if there are any snowstorms or snow or ice on other planets.
That's a great question. Yeah, so different planets can have different weather patterns. Like a lot of the gas giants, like Jupiter and Saturn, they have massive storms that are in their upper atmospheres. And so even though there's no solid surface, storms can still happen. They can still form just because of how much gas there is in the planet and how fast the planet spins. It actually makes it a very conducive environment for storms. So a lot of those types of storms are like hurricanes. But on Titan, for example, one of Saturn's moons, Titan has oceans and lakes and rivers of liquid methane on its surface. And so it has a whole methane cycle. We think it rains methane on Titan. Mars has dust storms. Venus probably has a lot of storms too, because it has a really thick atmosphere. There's probably some lightning going on in there. So yeah, there are a lot of other weather patterns. As for snow in particular, I don't know. Talia, do you know the answer to that? Or is there any kind of like, I know it probably wouldn't be.
I mean, not the way we see it on Earth, but so, you know, nothing like this storm that's coming up to Boston on Thursday. But for instance, you do see snow in certain places, the poles of Mars or even Pluto. There are places where the atmosphere can it gets so cold that the atmosphere can turn to snow and snow down on the surface. And that happens around the poles of Mars. It happens to Pluto. You know, we saw Pluto's orbit is really oval shaped, which means when it's really getting farther from the sun, it gets a lot colder than when it's closer to the sun, and its atmosphere turns to snow and snows onto the ground. So it definitely does snow places. It's just not really the kinds of snowstorms that we see here on Earth.
Not going to get any nor'easters on Pluto.
Probably not.
Very cool to think about, though. Snow on other places, other planets.
We've had a number of questions about aurora. Specifically, Allison, age 10, asks, why do the northern lights look green or blue? We also have some questions about can aurora borealis hit the ground? And where can we see them? And is it possible to see them in Massachusetts or even as far south as Texas? Someone is asking.
Yeah, so the aurora, the color of the aurora, it tends to be green most often because oxygen and nitrogen are the two most prominent elements in our atmosphere. And when those molecules collide with these energetic molecules coming from the sun, these charged particles from the sun, they tend to emit specifically green light. And that's not always the case. That's just the most common. There are some other variations of oxygen molecules and other trace gases in our atmosphere that will create other colors. So it's not always green, but that tends to be the most common one. But sometimes you'll see red or even like a purpley color sometimes too from other gases. It cannot reach the ground because it happens very, very high up in the Earth's atmosphere in a layer called the ionosphere. So this is a layer of Earth's atmosphere that is, I believe, like 80 kilometers up. I don't know what that is in miles, maybe like 50 or 60 miles up, I think.
This way, it's way above where airplanes fly.
Yeah, it's very, very high. And that's where all of this happens. And it's just so bright that you can see it very easily from the surface of the Earth. And then the last question, I believe, was where you can see it and how far south, or I guess if you're in the southern hemisphere, how far north can you go and still see them? It's definitely a lot easier to see the aurora if you go above the Arctic Circle for certain, up here in the northern hemisphere. If you get a really, really strong solar storm, like a very strong solar flare or a coronal mass ejection or something like that, if they're strong enough, then that can cause particles to travel not just to the poles, but also reach farther south. And so it's not necessarily dangerous, but you are able to see it. And actually, I think it was last week, this area in New England was in kind of line with where you might be able to see the aurora because there was a strong like solar flare. As far south as Texas, I'm not sure. It's definitely uncommon, extremely rare. if it has ever happened, but I'm not sure that it would ever get that far south. I don't know, Talia, maybe you have some more insight into that.
I believe the single strongest event that we know of in the sun's in human history, looking up at the sun, which was the Carrington event in 1859. I believe the aurora got as far south as the southern United States. So,
wow.
But that was also, again, that was an excessively powerful event. We don't want something like that to happen, to come our way, because it would really wreak havoc on our satellite network. So,
that's a good point.
I think it has happened.
Yeah, and there are certain times where it's more likely to happen than other times because the sun goes through cycles. So there are periods of high solar activity and periods of lower solar activity, and it generally happens every 11 years or so. Is kind of like the solar cycle essentially. And so when the sun is at a peak, we find that it has a lot of sunspots. I'll go back to the sun. You can't really see sunspots in this particular video, but sunspots are kind of those darker, cooler regions on the surface of the sun where the magnetic field kind of pops out of the surface. That correlates with the dark spots. And so during a period of high solar activity, you see lots and lots of these sunspots. And then eventually it reaches a period of low activity again. So it's during these high periods where there's lots of sunspots, lots of magnetic activity, lots of twisting and turning of the magnetic field lines that creates these solar storms and these solar flares that can cause the really strong aurora. And there is another spacecraft that I wanted to mention called the Parker Solar Probe that was launched a few years ago. And in 2025, it's going to get the closest to the sun of any spacecraft that we've ever sent to study the sun or anything. It's going to get within 4.3 million miles of the sun, which is extremely close. And it's going to study a lot about the sun's magnetic field and how it works, because there's still a lot that astronomers don't know, especially related to why the sun actually goes through these periods of high activity and low activity. It's also going to study the solar atmosphere, the corona, and why it's so hot, and what's going on with all the charged particles in that area of the sun as well. And so that'll be really exciting because we have a whole star. We have a whole star very close by, and we should study it. And that'll tell us a lot about other stars in the universe as well.
Thank you so much for answering all of those questions, Katie. I'm sorry to say that we're out of time and we do have unanswered questions, so I'm sorry about that. I'd like to invite our educators to say goodbye to everyone.
Bye, everyone. Thank you.
I would invite all of you to check out some of our resources online. Some of you asked specifically about other recordings that you can find. You can find those on our YouTube channel. You can check out live offerings at mos.org/mos@home. And if you're able to, you can support us, engage.mos.org/welcome. Also, Talia was using a software package called Worldwide Telescope to showcase some of those planets and images that you saw, and that's available free to download. So if you want to explore the solar system yourself using that software, the link is on this page. Thank you again so much for joining us, and we hope to see you next time. Thanks again.